Not exciting. Okay. All right. So last couple of days, I've taught you about what a redox reaction is, that we have to have an oxidation half and a reduction half, and that in the oxidation half and the reduction half, the electrons that are being traded have to be the same, and that's how we balanced our redox reactions yesterday using the half reaction method. So up to this point, we've talked just about what a redox reaction is. We've talked about how to balance a redox reaction. And so now what we want to talk about today are actually two things. We want to cover two things in today's lesson. We want to talk about how we're going to predict whether a redox reaction takes place or not. Because, of course, like any other chemical reaction, some of them are spontaneous and some of them are not spontaneous. And we're going to also be introduced to something called standard reduction potentials. And the term potential in that statement corresponds to a topic that you've learned in electricity that deals with the potential energy an electron has as it's being pulled, say, through a circuit. So when we're talking about potential, we're really talking about potential energy, and in the physics world, we call that voltage, all right? So when we're talking about standard reduction potentials, we're talking about the voltage that a chemical pulls or pushes its electrons, all right? So we need these two concepts in order to understand or predict whether a redox reaction will take place. Looking ahead till tomorrow we're going to look at something called galvanic cells, which are essentially the simplest version of a battery. And obviously the purpose of a battery is to produce voltage so that a device can use it. And it is from redox reactions and these standard reduction potentials that a battery gets its voltage. So when we're talking about volts here today, we're literally talking about the volts that that chemical could produce if we were to make a battery out of it. All right, so that's kind of looking ahead to tomorrow. So we're going to be needing these numbers, and that's the table that I just handed you guys earlier on, and that's what we're going to be making reference to. Okay, so I've simply got this slide just out there, and I really need to have you write it down. This really indicates to you how we look at these standard reduction potentials. All right. So I'll just let you write, and I won't talk, and then I'll talk about it in a moment. Yep.
Definitely has negative volts.
I will explain that in a moment. When you get to the bottom, you'll notice that I've addressed the negative here, but I can still tell you how you have negative volts, right? How can something have negative potential? Now, Appendix B7 in the textbook is a table very similar to the one that I've given you. The one that I've given you I found on a website, and the reason I wanted to create my own is because just for the sake of you guys having your data tables, I don't want you to have to continually flip in your textbook, then you've got the data table right there. Now, the table that I've found is a little more extensive than the one that's in the textbook. It just means it has a few more half reactions, all right? And actually, at this point, it's probably not a bad thing to look at that table if you've finished writing. Okay, only one of us is finished writing. But if you finished writing and you're starting to look at the table, you'll notice that these are all half reactions. They look just like the half reactions that we balanced yesterday before we added the two half reactions up in order to get the entire redox reaction. And if you're looking at the table as well, and if you're not, you're still writing, it's on the screen here, you'll notice that each of these half reactions have the electrons being added to them, which means they're all on the left, which means what half reaction is it when the electrons are on the left? Reduction, right? GR, right? Or RIG, whichever one you want to use. And so these are all reduction potentials. And that's true about all of the numbers on this sheet. They're all reduction potentials. And they're called standard reduction potentials because they're compared to something else. They've been standardized to a particular reduction potential. When it comes to potential energy, you may have learned in physics that potential energy is something that you always simply compare to a certain location or a certain position. Potential energy is something that's relative to something. So let's say that you were, on a cliff that was halfway up a mountain, right? And it looked something like this. And you were standing there on this particular ledge of the cliff, then you would have a potential energy relative to the top versus relative to the bottom, and they would have simply different signs. In this case, if you took your potential energy relative to the lower position, your potential energy is positive. You're higher up in the potential, scenario. But if you were to measure your potential energy relative to the top, then your potential would be negative. You'd be down in a hole, all right? So you can easily have negative potential energy. When it comes to standard reduction potentials, the potential isn't gravitational potential energy, but the potential is electrical potential energy. And so each of these electrons has a potential to do something, to either be pulled towards an ion or pushed away from an ion, all right? Now, the relative starting point for standard reduction potentials, kind of like the ledge that you're standing on, they've decided as chemists to use H plus 2 electrons, 2H plus, to make H2. They've decided to make that the starting point, 0. So in other words, it simply means that according to the rest of them, this really has no potential. Now it does, but potential doesn't have any meaning until we compare two locations, right? So what we're doing is, when we put the standard reduction potentials, it's like we're putting everybody on a ladder with each rung representing a certain potential to grab up electrons, with H2 as being defined as the 0 point. Anything above H2 will have a positive reduction potential, which means this copper 2 wants to pull on 2 electrons. It has a pull on 2 electrons compared to hydrogen, all right? But if a potential has a negative, it means it doesn't want to pull on electrons. It means that this zinc actually wants to get rid of its electrons compared to hydrogen, all right? Because you must always compare two locations on the grid to see whether one is higher or one is lower, okay? So the way we're going to think about this is that H is our standard. It's just simply our middle rung. Anything with a positive voltage means that it wants electrons, and anything with a negative voltage means it really wants to get rid of its electrons, okay? All right? And that's because we're comparing it to hydrogen. So you can think of the positive as being that it pulls on electrons, it wants to be reduced, but the negative, you can think of it that it would rather push its electrons away. If it was compared to hydrogen, it would rather be oxidized, okay? There's a simple fix. If we have a negative potential, If we flip the equation around and now put the metal on the left in the terms of zinc and put our zinc ion and electrons on the right, I've now changed my reduction potential to an oxidation potential. How good it would be at getting rid of its electrons. And when you flip the equation, you change the sign. So this means that zinc metal, would prefer to get rid of its electrons compared to hydrogen. Now, I'm not going to say compared to hydrogen every time, but that's what it is. That's why we have hydrogen as 0, 0, 0. So when it comes to potentials, positive is good. Positive is spontaneous. Negative isn't spontaneous. That's true for standing on the cliff as well. If you're standing on the cliff and you have a positive potential with respect to the level below you, falling off the cliff is spontaneous. You don't want to do that. Might not land very well, right? But in the end, you spontaneously fall off the cliff. If you have a negative potential compared to the level you're interested in, rising up to a higher level spontaneously is not going to happen. You never fall up a cliff. It's a non-spontaneous interaction. So it's exactly the same. Positive potentials are a spontaneous thing. Negative potentials are not spontaneous. It doesn't mean that they can't happen. It means we would need to put some energy in to push it, to happen, but it wouldn't happen spontaneously. Okay? Now, how do we then determine whether an oxidation reduction reaction is spontaneous or not? We have to put a reduction potential with an oxidation potential, because we have to have an oxidation half and a reduction half. When you put your two half reactions together, you get an overall delta E for the overall reaction. And that's the important part. It's the difference in potential. It doesn't matter where you are on the rung of the ladder. It's how far apart you are on the ladder that counts. I'm hoping we realize that when I put red half, it means reduction half, just for the sake of saving a few letters. We want to conserve letters. Letters are running out in the world and we don't want to use them all up. So in my course, I like to conserve letters. So when we put a reduction half together with an oxidation half to create a redox reaction, the overall potential difference, which is essentially like the separation in the ladder now, and that's not looking at hydrogen anymore. In other words, we're just looking at how far apart they are on the ladder, okay? Gets us the overall delta E. Now jumping ahead to tomorrow, if we were to make a battery out of that, that delta E is how much volts that battery could provide you. It's actually called a cell, all right? A cell is a single part of a battery. When you put a bunch of cells together, you make a battery. We'll talk more about that, but I'm going to talk cell now in terms of that. So if you had these half reactions and you made a cell out of them, that's what voltage would be produced. Actually, tomorrow I'm hoping that I quickly teach you about the way a cell works, because we really don't have anything new to learn. We are using the same concepts we're doing today. And then, as a quick little activity, I'm going to get you to make some cells, and using some voltmeters, we're going to measure their voltage, and we're going to see whether we're close to what it actually is supposed to be. What's that? No, we're not going to use a lemon. Goodness, we'll save that for like grade 9s. We'll actually use some real chemicals. Okay, so if the delta E for the reaction is positive, it's spontaneous. It means that the electrons are moving from the high down to the low. They're falling down the potential, and it's going to spontaneously do that, and the reaction's going to happen. If, when you do your calculation, you get a negative, then it means that the electrons need to be pushed up an energy hill. not spontaneous. You could do it. You could plug it in. You could provide some electrical energy from another cell and push it back the other way. We're not going to talk about that in this because we're going to run out of time. But that you can do. You can actually force chemical reactions by putting electricity in and pushing the electrons the other way. That's what happens in something called a Huffman apparatus. In grade 9, your grade 9 teacher might have shown you the Huffman apparatus. It would have looked like this big letter H type thing. It has a container for the acid, and it's got a container here like this, and then it's got another one here, and then it's got some electrodes in here, and then you plug this thing in, and bubbles form, and it's got a tap on the top, and then it takes the water and it breaks it into that much and that much, and that much is oxygen and that much is hydrogen, and you go, ooh, ah, isn't chemistry awesome, right? You've seen that thing before, right? Because you get 2 parts hydrogen and 1 part oxygen, and it's H2O, and you say, wow, science is awesome, right? And what this is it's taking the reaction that forms water, and it puts electricity in, and it pushes the electrons back where they came from. And it does a reverse redox reaction, because the spontaneous reaction is for the hydrogen and the oxygen to get together and form water, but the non-spontaneous reaction is the opposite redox reaction to separate them out. So you can put electricity in and fight that. We're not going to deal with that right now. Okay, so essentially what do we have to do? In order to determine if a reaction is spontaneous, it's very simple. We need to break it into its half reactions, like we did. We need to find those half reactions on our page. We need to write down the potential. If one of them is flipped, we need to change the sign, and then we need to add the 2 numbers together. And if we get a positive, it's spontaneous. And if we get a negative, it's not spontaneous. It's pretty straightforward stuff. All right, so let's go ahead and take a look at some of this. So let's take a look at this example first. So we'll put EG. You can write this down, and I'm going to just break it into the half reaction, and you're going to do the same. So this is zinc solid in a solution of copper plus 2 ions. And we want to know whether this is going to result in really, this is the net ionic equation for a single displacement reaction. So let's break this down. Let's see if my pen is going to work here today. So Zn solid, and that's going to become Zn plus 2. And I'm not worried about the aqueous in the solid. Really, I know that this is a 0 charge. This is plus 2. So where do my electrons go? On the right-hand side. Plus 2 electrons. And let's not go looking for that on our potential sheet yet. We'll take a look at that in a moment. So next we're going to have Cu plus 2, and that's going to become Cu0. And where do the electrons go for that? On the left. Excellent. So we've got 2 reactions here. One is a oxidation half, one is a reduction half. And actually maybe we'll put that. This one, what's the top one? Oxidation, and this one is reduction. Okay, so now let's go to our page, and this is where I don't know whether my technology is going to work for me or not. Oh, look at, now I'm writing on this, and I'm not dragging. Oh, and now I've got a yellow line there. That's awesome. We'll just ignore that yellow line, because I don't know how to get rid of it right now. Actually, I might be able to get rid of it. Let's get rid of that yellow line. Ooh, fun. All right. Okay, so let's take a look at this page here before we get going. Let's go to the very bottom. Take a look at this down at the bottom. Lithium plus, potassium plus, calcium plus. These are the highly reactive metals. Remember that on our activity series? They stood at the top. Notice their potentials, negative 3.05. That means a lithium ion really has no interest in that electron. A lithium ion does not want to be reduced to become a lithium atom, because it would rather exist as the ion. Remember, they're highly reactive. So down here at the bottom, or below our water, or where's our hydrogen? Our hydrogen is right there. Below our hydrogen are the ones that want to be as ions. They don't want to be reduced. These negative guys, they'd rather be flipped and be oxidized, okay? If we go to the top of the reaction, you'll see here things like silver. Remember, silver and gold were at the least reactive. So these guys, if you have, let's see if I can find gold. Here's gold right here, gold metal. If you have a gold ion and you give it the opportunity to gain 3 electrons, it will become a gold atom, and it will do so with a voltage of 1.5 volts. That's spontaneous. It would rather be as a gold atom, okay? So these guys here with the positive E are very good at being reduced. They like being reduced. This F2 wants to be reduced. This AG wants to be reduced, all right? If the thing wants to be reduced, remember, it makes it a good oxidizing agent, right? It's a good oxidizing agent. So our good oxidizing agents are over here, and our good reducing agents are on the other side. We don't need to have that all in our minds in order to answer the questions, but that's the way it works out. Let's go ahead and find our 2 pieces of data. So I need a copper, and I already know kind of where this goes. Look at here. Here's a copper 2, but notice it gains 1 electron to become a copper 1. That's not the reaction we want. We have to have the reaction where it becomes copper 0, the metal. So let's keep looking here. Here I've got copper 1 becoming copper. Oh, here we go, right here. Here I've got copper 2 gaining 2 electrons to become copper metal, and you'll see here the number is 0.34. Everybody spot that? Can you all see that? So now I can swap back to my PowerPoint here, and that's the exact same as the copper ion wanting to become copper metal. It's not being flipped, right? This is reduction. So my potential right here, I'll write it off the side, 0.34 volts. Everybody see how I did that? Went to the table, found the exact reaction, wrote it down. And it has to be exact. It can't be copper 2 becoming copper 1. That's a different version of reduction. It's being reduced just to the copper 1 ion, but we want to reduce it all the way down to the copper 0. Okay? How's it going, Jamie? Okay, let's find the other one. Zinc is fairly reactive. You can see here, if you take a glance, we've got a zinc sulfide, and here we've got a zinc with an ammonium stuck to it. That's not what we're looking for. Again, excellent stuff. I'm writing lines on this. Oh, and now I'm moving the lines. That's fun in a non-fun way. Get out of here. Has anybody found the zinc? Excellent. That's fine, because these are reduction potentials. And so we expect it to be flipped. So there's Zn2 plus 2 to become Zn. And so we're going to flip it. It's negative 7.6. Sorry, it's negative 0.76. So when we flip it, what am I writing here? Yeah, and I'm going to just put here negative 0.76. Now, you don't have to write it that way, but I'm just illustrating that we flipped it, so I put the negative in the front, and that was a negative, and now the negatives are gone. We're okay with that? So now let's add up oh, that's a terrible horizontal line. I'm not very good at this device. Let's add up the 2 values. What does that get me? That's a 1, and that's a 0.1. Oh, no, that's not. It's exactly 1, isn't it? 1.0. No, it's not. It's 1.1. Oh, see if my eraser works. I got sucked into that. I won't tell the world who told me to write that down. 1.10 volts. All right? 1.10 volts. Is this spontaneous? Is this going to happen? Yeah. Yes, it is. It's positive. So this thing is positive. Therefore, it is a spontaneous reaction. That reaction is going to happen by itself. Okay? Pretty straightforward business. Now, of course, it's not that easy. It's going to get more complicated. We're going to have some more complicated ones. But that's the starting point of it. Now, all I'm doing for the second example is I've flipped everything. All right? This saves us from having to look for some new numbers, but we will have to. So notice, Now let's say I have some copper solid in some zinc ions. Last year we would have used the activity series to see which was below, but now this year we're far more advanced students. We know we have to use reduction potentials. So again, I'm just going to write the whole thing out. Zn plus 2 to become Zn solid. This time I need the 2 electrons here. And its potential was, I think, negative 0.76, correct? Because it's now the reduction one. And then our copper solid is becoming copper plus 2. And I need my 2 electrons here on that side. And that one was, what was it? 0.34? Was it 0.34? But I flipped it now, right? So it's actually negative 0.34. And now when we add those, we get negative 1.10 volts, obviously, which is fine that I used an obvious one. And when you get a negative there, it is not spontaneous. All right? Now remember earlier in the course when we talked about delta G? Good times with delta G? And if we had a delta G that was negative because the energy was coming down, it was spontaneous because we were talking about falling energy. Voltage, we do it opposite, right? There are equations that relate delta G to these potentials. In university, you will learn the equation that actually relates the delta G to potentials because they are really talking about the same thing. They're just talking about it in a slightly different context. So there are equations that relate those things. They're kind of neat. Okay, let's keep going. So let's now do some more complex ones. So here we've got some aluminum with some copper sulfate, and then some copper, and it's becoming then aluminum sulfate. Okay. I'll let you write this. I see that you're writing. I'm just so excited. I haven't taught this in a while. I want to get going. It's good. It's fun. Now notice in these questions, I'm not asking in the end for a balanced chemical equation. I'm not concerned about it being balanced. I'm just concerned about whether it's spontaneous or not, all right? So I'm not going to bother balancing this equation. We don't need to worry about that. So what's the spectator ion in this particular substance? Yeah, the sulfate. Excellent. The sulfate is the spectator ion because I'm going from aluminum, which has an oxidation state of 0, to some kind of aluminum, which has an oxidation state of 3. So let's break them into the half reactions, where we're going to take aluminum. We're starting with aluminum solid, and it's becoming, what's the charge on these aluminum ions here if we do our reverse crossover? 3, and that's what aluminum is, aluminum plus 3. So Al plus 3, and what side are my electrons going on? Right, plus 3 electrons, and therefore, what is this half representing? Oxidation. Oxidation. What's the charge on our copper in the reactant side? Plus 2. Becoming Cu solid. My electrons have to be on this side, right? I need 2 electrons over here. Plus. And therefore, that's the reduction half. Now notice, I've got 3 electrons up here and 2 electrons down here. I don't mathematically have the electrons the same, but we're not balancing. If we wanted to balance, we could add these 2 half reactions just like we did yesterday. I would multiply the top one by 2, the bottom one by 3. We would have 6 electrons. I'd then, cancel things out and away we would go. But when it comes to spontaneity and when it comes to the voltage, it doesn't matter how many electrons are moving. Physics-wise, voltage is equal to energy divided by Q. Q stands for the charge, all right? And what that means is each electron carries that energy. So it doesn't matter whether there's 3 electrons or whether there's 2 electrons or whether there's 1 electron. We're talking about the energy on a per electron basis. So it doesn't matter whether there's 3 electrons, 2 electrons, or 1 electron. It doesn't affect the V that we write down here. We don't divide it or multiply it or anything like that. So let's go to our table. Has anybody tracked down the aluminum reaction? Anybody find the aluminum reaction? I spotted it already. I got it. Nobody else? No? Did you find it? It's in the right column down here, over here. Excellent. Aluminum plus 3 electrons to make aluminum. We have a flipped version of that, don't we? So our negative 1.66 is going to be 1.66. So right here we've got 1.66. I'm not putting negative times 1.66. I think we get the idea, right? Let's find the copper. Well, we've already done the copper, right? So I am moving to this side of the page, I think. Oh, that's copper 1. Oh, there's copper 2. 0.34. We had that number, right? It's a non-flip, so it's staying the way it is. So 0.34. And even before we get calculating here, we can tell whether it's spontaneous, can't we? They're both positive. This is going to add up to be positive. Let's, though, calculate how many volts this would produce if we could make a battery out of the copper and the aluminum, which we could. How many volts is that? What does that add up to? Exactly 2? I didn't even, that's exciting stuff. Volts. Okay, so therefore positive, therefore spontaneous. Awesome. There's no panic in our faces yet at this point. Have you already done the second one? No. Oh, no, it wasn't much harder. Nope, it's not this either. It's, again, don't write down, determine the whatever, just write down B. I cut and pasted slides here. Right, we're determining the same spontaneity, it's just B. No, it's the number 2 questions that are much harder. Hard but fun. Fun because it's hard.
Is it your idea fun or our idea fun?
I don't know. You've got many years of university ahead of you. Things will be hard. If you don't have fun, it's going to be a long time.
I like to something to get to.
So have fun. Have fun as you work. Think of learning as fun. I loved it. I always thought, I'm becoming smarter than someone else. I don't know who that is, but I'm smarter than somebody. And the more I learn, the smarter I'm moving up the chain. Thanks for bursting my balloon there. That's what got me through university, thinking I was becoming better than somebody else. Oh well. Okay, so let's break this into half reactions. Mg. Again, you don't need to write the solid. You don't need to write the 0. If you need to help you out, that's great. That's becoming, notice, nitrate. I hope we're thinking nitrate's the spectator ion without me asking. So this is becoming Mg plus 2, and I need my 2 electrons over there. And what is that half? What do we describe this half reaction as? Oxidation. Oxidation. And our K plus, and that's becoming K0, and my electron is over there, and that's reduction. The reason I like to do that is the reduction one, you're looking for it and you're just using the number. The oxidation one, you're changing the sign, right? So let's go hunting for some ions here. Which one?
Right side. That's where the bottom.
And what ion are you dealing with? Magnesium, or you found magnesium? Right there? Do you see my hand? Isn't this fun? I'm waving to people on TV. Over here! Okay, all right. So magnesium, and it's 2.37, and we flip that guy, so we need to switch the sign, right? So we flip that guy. So negative 2.37 becomes positive 2.37, 2.37, and now we're back for the potassium. And you might think, oh, positive 2.37, this is looking good. Could be spontaneous, it's big. Where's the potassium? Down at the bottom. And this is the reduction potential. We don't need to change sides. Negative 2.92. And so negative 2.92, negative 2.92. And so like I said, it's not necessarily the potential itself, but it's the relative potential. This may want to spontaneously happen, but the opposite pull is so strong that it won't let that happen. So what do we have here mathematically? Somebody calculate that for me. Nobody's got calculators out because we've been like adding to 2. Negative 0.55. We're using Jason's awesome mental powers here. I believe him. He's done this 5 or 6 times and he's always right. It's always right. We don't even bother checking. We're going with good. So obviously, is this going to take place? No. All right. So not spontaneous. So now, remember when I used to say if it's at the bottom, it wants to be alone and its relative positions, right? It has everything to do with that, how strong it's pulling on electrons and its potential to pull on electrons, okay? Let's now do some more that are more harder. Can I say that? More harder. Yep. And it's a good thing my wife doesn't watch my videos or she would be critiquing me. Harder, more harder. That's what you wanted me to say? More harder. That's more betterer. Thank you. All right. It's funny when I edit them. Are you listening to yourself in there? Oh, I should watch it. I'm videotaping this. If I put this on, so maybe she will watch it someday. Okay, so this becomes a little tricky because I'm not telling you what the products are. And we've got potassium ions in there, which could become potassium metal. Not likely, right? But it could. We've got these permanganate ions that can do something. We've got hydrogen ions that could do something. And we have sulfite ions that can do something. All right? And we also have water. Because if you take a look at your page, I don't know if you've spotted it, but water is in here as well. Let me find one of the versions for water. Where is it? It's in here somewhere. Where's the water? Right here. Look at here. Water can gain 2 electrons, be reduced, and become H2 and produce some OHs. All right? Over here on the other side, and now I got to find the water, and I think it's, where is it? Is it up near the top? Did you find it? It's down? Did I miss it? Starts with an O. No, that's not, this is H2O2. There's another one. You're right, it does start with an O. There it is. There it is. There it is. So water here, but there's no oxygen. There's going to be no oxygen in that solution. There's no oxygen whatsoever, so that one doesn't count. Over here. Water all by itself can then break apart into this. All right? Because remember, we can flip them. We can flip them. Okay? So water can always be oxidized and water can be reduced. And because this is happening in an aqueous solution, water might get involved in the game. So how do we go about solving this? Well, what we do to begin with is we make a list of all the things that are in the water. It's kind of like going back to the acid-basis stuff. What's in the water? So we're going to just make a list of what's in the water. And it's only the reactants we're writing down. So, K+. In a moment, I'm going to turn that into an oxidation reaction or a reduction reaction. I'm going to add to it. But right now, I'm just listing. We've got an MnO4- ion. I think it's a permanganate ion. We have H+. All right? We have SO3- 2. We have H2O. H2O that can be reduced. And we have H2O that can be oxidized. We're always going to have those two. They're going to be the same two, because We don't have any oxygen in here, so we don't have to worry about the water plus the oxygen. We can only have in our equations any of these things. Also, we can have H pluses, because that can come from water, and we can have OHs. Remember, that can come from water. Okay? They can be in there as well. So let's now go searching. We actually have seen this one, right? It can turn into just good old K. Okay? And it needs to have an electron added to that. All right? You know what? I'm going to have to do this a little differently. I maybe should have written this down as a reaction off to the side. I'm going to do that for the rest. I'm going to just put like a colon here around each of these. So in the end, I'll write the reaction that goes with it. Okay? All right. So I guess to fix this up, let me just get rid of this. I'll write the electron plus K plus to produce K. Okay, makes sense? Let's go hunting for the MnO4. Now, it can be on either side, all right? And it can't have anything other than like an H plus or an OH, you know, those types of things. So take a look here. I have an MnO4 with some waters, right? That's a good one. That would count. Let's see if there's any others. Here I've got an MnO4 with just an electron. That could count. That would be good. It could be either of those two. Now I'm not going to write it down yet, because notice the one above it has the higher potential. And so it's going to happen more preferably than this one, because it has a greater potential. So we're not going to count this bottom one. Let's see if there's any others. There's one way up at the top. Yeah, excellent. Oh, that's MnO2. Above it, still. Oh, there's an MnO4. H pluses, that's fair game. It turns into Mn plus 2, and its potential is 1.51. It's the highest so far of all those. Notice we haven't had to flip anything. They all have them on the left. So even though MnO4 has the opportunity to do 3 different reduction reactions, it's always going to be the most energetic reduction reaction, so we can pick that one. There's another one above it. Oh my goodness. MnO4 to go to MnO2. That's awesome. We're even higher energy. Are there any more? We're almost to the top. Excellent. That's the one that's going to happen. Let's write that reaction down, and then we'll go searching for the rest. So once I spot it, I write the reaction down. And what do we have? Oops, need a pen here. MnO4 minus. We're adding 4 electrons. Oh no, 4 H pluses. I'm having difficulty erasing. 4 H pluses, 3 electrons, becoming MnO2 and 2 waters. We don't care about the product side because that's what's formed. We're trying to figure out the products as well. Let's look for H plus and SO3 minus. Now H plus is that one in the middle, H plus, and it's going to become H2, right? That's that 0 voltage one. We need 2 of those. I think we need 2 electrons, right? And its voltage is 0. We know it's there. It's that guy that's on the right-hand side near the top, right? We'll go get. Actually, let's write the potentials down as we're doing it. 0.00. What was the potential of that MnO4 one near the top? 1.68. And what's the potential for the E plus to become K? So you'll notice we're starting to get a list of what's likely going to happen and what isn't going to happen. Let's keep going. SO3 minus 2. Now you might spot an SO4, but that doesn't count. See, there's one right there. We don't have an SO4, we have SO3. It can be on the left or the right. Where? Bottomish middle, and we're looking on the left side. SO3 plus 2OH to become SO4. Yep, we can do that reaction. That's a fair game. I've got some mild concern here for a moment, though. Yeah, I do have mild concern on this one. Because I said OHs were fair, but this isn't in a basic solution. Does it say what the solution is? Doesn't say. If this were in a basic solution, it would be the 1. But if it were, we need to know whether it's acidic or basic, because take a look over here. Take a look at this one. Look at, I've got something that actually contains H2SO3. You see what I mean? It actually contains the H2SO3, and we can use that. That's one of our reactants. So what we choose here, I guess, needs to be determined by whether we're in an acidic or a basic solution. I should have stated that before. What would you like this to be? Let's do it acidic. In acidic. Because that then eliminates the OH one, because there wouldn't be enough OH around. Okay? So we're going to use this one here. Right? We're going to use this guy here, because we've got lots of water around. So let's flip him around. H2SO4, or H2SO3 plus water. H2SO3 plus water. Could somebody tell me what the product side is so I don't have to flip? Actually, I've got my sheet right here. Is it SO4? SO4, 2 minus 4H plus, and 2 electrons. And we flipped this, didn't we? So what does it make it? Negative 0.20. Excellent. Now we have to find our 2 water ones, which is the oxidation and the reduction. And I've pointed those 2 out, and I'm going to just go to my page and not flip. Where is that guy? Over there on the right. Where's our water guy? There it is. 2 waters plus 2 electrons. So 2 waters plus 2 electrons to produce H2 gas. And I'm not worried about the sign, or the states. Plus 2 OHs. And that is not been flipped, right? Correct? Not been flipped? Negative 0.41. And let's find the other one where the water's on the other side. And we do have to flip it. H2. And that becomes half an O2. 2H plus. And 2 electrons. And that has been flipped, so it becomes negative 0. And is it an 8.2? 8.2? Okay. 8.3? 8.2. 0.82. Okay. All right. That was fun, right? So we had to spot all those things. So now what we need to do is we need to state whether it's a reduction half or an oxidation half, because we have to pick one reduction and one oxidation. Okay? So what is this guy? Reduction. How do you know? You know this. Yeah, it's gaining electrons. The electron's on the left. What's this guy? Reduction. Its electrons on the left as well. What's this guy? Reduction. And this guy? Oxidation. And this guy? Reduction. And this guy, oxidation. The pair that will give us the greatest delta E will be the pair we choose. The way you determine that is we simply need the ones that are the biggest, the most positive. So what happened to my slide? Did I advance? That's catastrophic if I lose all this writing. Like, what's my computer doing? Okay, so let's look at all the reduction ones. Reduction, reduction, reduction. Which one is the most positive? The second one, the MnO4. So, not going to happen. Now I can't, lost my pen here. Not going to happen. Not going to happen. Not going to happen. That guy is going to happen. Because it's the biggest and most positive. Okay? Put a check mark beside that one maybe. Whatever you need to do to bring your eyes to it. How many oxidation ones have we got to choose from? Only 2. Which one is going to be the most positive? Or which one is the most positive? The H2SO3. It's going to happen before this one happens. So this one, not going to happen. That's going to happen. There's our 2 half reactions. Now we're going to just rewrite them and put them together. Those are the 2 that we're going to choose. And now I'd like to advance my slide. And if someone could tell me, as you're rewriting, because I don't have my slide in front of me, we got MnO4. Somebody tell me. Carissa, go ahead.
MnO4 minus plus 4H plus
4H
3
plus 3 electrons. To produce
MnO2 plus 2 water.
1 point. As soon as she's caught up. 6.8.
And then for H2SO3.
H2SO3.
Plus H2O.
H2O.
To produce SO4 2 minus.
SO4 2 minus.
Plus 4H plus.
4H plus.
Plus 2 electrons.
Plus 2 electrons. Negative 0. I think it was 20? 0.20. All right. For the final check to see if it truly is spontaneous, because sometimes even if we pick the most positive ones, they may still add to be a negative number. This isn't. This is going to be what? 1.48 volts? Will this reaction happen? Yes. Yes, spontaneous. Yes, spontaneous. Okay? Now to balance it. To balance it and come up with the final answer, we're going to do exactly what we did yesterday. We have our 2 half reactions. And these half reactions are balanced. Really what they've done is they've taken those half reactions we did yesterday and they've checked all the voltages for them. That's why they're here. So all I need to do is take a look at my 3 electrons here and my 2 electrons here, and I'm going to do just like yesterday, times 2 and times 3, and I am going to add them all up, and I'm going to cancel anything that's redundant on both sides, and I will have achieved also a balanced chemical equation. So I'm going to just roll on through here. 2MnO4 minus plus 8H plus. The electrons are gone. I'm going to go to the other side. Here, I'll cancel those electrons out, 6 and 6. I'm going to go to the bottom one, plus 3H2SO4 plus 3H2O. I'm at the middle, 3SO4 minus 2. 4 times 3 is what, 12? 12H plus. The electrons are gone. Back up to the top. 2MnO2 and 4H2O, and I'm really close to my words that say yes, spontaneous. And what can we cancel? Some waters, I think, right? 3 waters there, gone, and that 4 is going to then become a 1. 1. Right? And I've got 12 H's on this side. Ha! Look at what I did. I did exactly what I did yesterday when I did this as a practice, and I screwed it up because I did this earlier on. I turned that SO3 into an SO4, and then it doesn't balance. That'll fix it. So what am I doing with the H's here? 12 and 8, so these 8 are gone. And what have I got left here? 4? 4. So one final time, we'll do a rewrite. 2MnO4 minus, plus, the H pluses are gone, 3H2SO3. The waters are gone, which means I don't need a plus. I need an arrow. To produce 3SO4 minus 2 plus 4H plus 2, and that's not an M, MnO2 plus a water. That's fun. Yeah, okay. Now, looking at the time, I did have a second one. This one is non-spontaneous. I'm not going to do it. We would have just been fishing and looking for the same things. You wouldn't need to balance it. You would need to complete it. What would happen is when it's non-spontaneous, you end up, even though you've picked the most positive ones, they both add up to being a negative number. It's not going to happen. No need to complete it and balance it. Okay? What's that? You'd be doing the same. You'd be taking an accounting of all of the possible ions. So let's just discuss it. Because it's an aqueous solution, water is around, and water can be reduced and it can be oxidized, as we can see, and it has a potential. And therefore, let's say we put it with something that is weak. If the delta E is such that when you have water as one of the highest and it becomes positive, it will react with that water and things will happen. Because water can be reduced and it can be oxidized.
So we just need one that's oxidized and that's reduced.
That's right. Because if you flip it, you end up with reactants that don't exist. If I flip this, all right, then my reactant is H2, right? You see here? And there is no H2 here in this aqueous solution. There's no H2 around. And so it can't possibly be one of the reactions. So you need to kind of look carefully at the reactants, and if you're flipping it, it's the products, right? They must be part of our list in order for it to be valid. That's why I had to get rid of that one with the OH, because we have H+. I didn't need to state that this was acidic. That's why I forgot about it. Look at, it's in an acid. So we needed the one that had the H+ in it and not the OH, because it was in acid.
Okay, so the reactant side
has to be the ones that are in that list, right? Okay, so if we're looking at this one, Na+, and then the iodate, and Mg+2, and Cl-, and the two waters, always the two waters. And the two waters will always be the same two if it's acidic, right? If it's acidic, it'll be those two. If it's basic, it would be that one with the OH instead of the H+, right? So there's always an oxidation half for water and a reduction half, okay? And then you just need to pick the ones of the reduction type that has the highest and the one of the oxidation type that has the highest. And if it adds to something greater than 0, spontaneous. If it adds to something less than 0, non-spontaneous. Okay, so there are some practice problems there, and we're done. Successful video.